I want to talk about survival analysis today. Now, many of you in past epidemiology or perhaps biostatistics classes have been presented with sort of a table that says if your outcome data is binary, this is the kind of regression you do. You do a logistic regression. If it's continuous, you do a linear regression, etc. And on that table, there's a category that says time to event data, and it tells you that you do a survival analysis. And what always puzzled me was then when you got to look at survival analysis, the outcome wasn't time to event at all. And why is that? So I want to go over that today as part of our introduction to survival analysis. And the way I'm going to do this is I'm going to start with a data set, and we're going to work our way through it, starting under the assumption that what we want to know actually is time to event. Because after all, nobody ever walked into their doctor's office and said, "Doc, if I quit smoking, what is that going to do to my hazard rate?" They want to know, how many more years will I live if I quit smoking? Why don't we do the analysis and give them the answer? So I'm going to start with a data set from the first National Health and Nutrition Examination Survey, and I'm looking at a subset of that data set, all of whom died on follow-up. Why? Because many of you may have been told that the reason we don't analyze time to event as our outcome is that we don't observe it for everybody. Failure times are censored. So I'm going to start with a data set where that's not true, and then we'll see what we can see. We'll go on. We'll start making that assumption true. We will have missing failure times. We'll see what that does, and then we'll get to what I think is the actual reason that in epidemiology we often don't look at failure time as our outcome variable. Okay? So let's start. Okay? We really would prefer to model failure time. That's what people want to know. How do these covariates affect my life expectancy? And so we want to know how failure time depends on risk factors. And as I said, we're going to look at this data set where there's no censoring to start with. So here's some summary of that data set. What you can see is the mean of various variables. So that, for example, age is the age that they were when they were recruited into the cohort, when they were examined in the NHANES 1 initial survey. Okay, and you can see it goes from 25 to 77. Okay, and then we have body mass index. Okay, and then we have various other variables that may be less clear to you. Booze is a categorical variable for the amount of alcohol intake. Education is a categorical variable for how many years of education. Family income, FAMINC, is a categorical variable for level of family income, etc. SED rate is sedimentation rate, which is a marker of inflammation. SEER-CHOL is serum cholesterol, etc. And we have 4,604 people, all of whom died. We have 4,604 observations of the variable dead, and it's always 1. And we have the year in which people died for everybody. Okay? So we've got this data, and we're looking at the age at which people died, the outcome they're interested in. In SAS, we can use proc-GLM. We could also use proc-reg, but proc-GLM allows you to use a class statement, so you don't have to generate your own dummy variables. And so we're going to put various categorical variables in that class statement: sex, a race variable, and the reference is going to be 1, which is whites. You need to tell SAS what the reference category is, because SAS's default is weird. Often used to diagnose an acute infection when it's high, but when you don't have an infection, it may tell us something about the inflammatory state in your body. Okay? So those are variables that we have in our data. It's a continuous number, and so it makes sense to treat that in a linear regression. So we could do a linear regression for the age at which people died as a function of predictors. So as we've discussed previously, they always choose the reference category to be the highest value. Okay? Booze, education, the reference category is going to be 1, which is the lowest education category, etc. And then our model is we're regressing age at death against predictors. And the first predictor in there is age. Age, remember, is the age at which they entered the survey. Okay? And I put in also a quadratic term for age because I think that mortality rates may not change linearly with age, and therefore life expectancy may not vary linearly with age. But we can check that by looking at what we see with these variables. I've got sex, race, obesity, booze, marital status, education, serum cholesterol, which I've also put in as a quadratic term, family income, and sedimentation rate. So that's a standard linear regression that we can do in proc-GLM. And what do we find? Well, let's take a look. Now, for age, notice that the coefficient of age is positive, but the coefficient of age squared is negative. Now let's think about that for a moment. Why would the coefficient of age at which you enter the cohort for follow-up be protective? Right? It's associated with a longer life expectancy. Well, if you enter the cohort at age 60, you can't die at age 50. So the older people are when they enter the cohort, the longer their life expectancy is probably going to be because they've already lived past earlier life expectancies. And so we might not be surprised that age at entry has a positive association. But eventually, right, if you enter at 85, you're probably not going to live that much longer, alas. And so that effect starts to diminish, and that's what the negative sign for age squared tells us. It says, yeah, there's this tendency to live longer to an older age if you started at an older age, but that starts to diminish as you go up in age. Okay? And so that's why we see that, and we see that the National Center for Health Statistics falls in the, remember, there are two kinds of people who think that yes/no variables are 0 or 1, and people who think they're 1 or 2, and the National Center for Health Statistics falls in the latter group. And you can also tell by the fact that sex 1 lives 1.4 years less on average than sex 2, that sex equals 1 is males. Okay? And then we have these various other factors. You can see, for example, that the more money you have, the longer you live, etc. So, that's great. Everybody's died. We've observed the follow-up time. We've done this analysis. But after all, many people don't want to wait till everybody in their cohort has died because they might die first. And so we often analyze cohort data when some of the failure times are not observed. So what happens then? Is that the reason that we're not going to use age at death as the outcome variable in survival analysis? Well, what happens if they're missing at random? Let's take a look. So this is the simplest scenario. Yes, some people, I didn't get to determine what their age at death was. They were censored. If the censoring is random, here I'm creating a probability of being censored, and it just has some numbers in there, right? There's no variables. So it has nothing to do with anything. And then I generate a missing value indicator, which is a random binomial observation, a 0-1 observation with that probability. And then I take the means of our data set to take a look at those data. So P-miss is the probability of being missing. Miss is the realization of that. Either you were missing or you weren't for each of the 4,604 people in the cohort. And what you see is that about 17% of the observations are now missing. Okay, and so now I can redo my analysis and see what would have happened had 17% of the failure times been missing, but they were missing completely at random. So here's how I do that. I go back to proc-GLM, but now I say where miss equals 0. So I'm dropping all the people for whom this random variable miss was 1. Those are my people whose failure times are censored. Okay? And I do the same regression analysis, same variables. What happens to the results when 17% of the failure times are not observed? Well, here's what we get in the old analysis and the new analysis, respectively, and these numbers are essentially the same, right? This is 1.19 with a standard error of 0.09, right? So, you know, the confidence interval of this is going to be about plus or minus 0.2, And clearly, this is not different. And the same with these. And here there's a little bit more difference, but remember, here's the standard error, right? So plus or minus 2 times 0.24 is plus or minus 0.48. These differ by 0.1. They're not different. So if I have censored survival times, and I just say, okay, forget them. Let me do the complete case analysis. Let me just analyze the people whose failure times I have. There's no bias in the estimate. I get the same coefficients. Well, that's interesting. But of course, these people were missing at random, right? What if that's not true? What if the older you are or the younger you are, the more likely it is for me not to observe your failure time? Okay? What if being missing depends on some of the predictors? Possibly the predictors that I'm interested in for doing my analysis, the exposure of interest. Well, let's take a look. Suppose I generate a probability of being missing that depends on age and obesity. Notice, by the way, that this equation is the same one you see for the probability in a logistic regression. A logistic regression, which when applied to a cohort, we can actually estimate the probability and not just the odds ratio, and it's e to the b0 plus b1x over 1 plus e to the b0 plus b1x, and that's what I've got here. So this is estimating the probability of being missing as a function of age and obesity. Then I calculate a random binomial variable for each person in my cohort using their age and obesity to estimate their probability of being missing. And then the realization is I either get a 1 or a 0. I take the means, and I get about 17% of the observations of failure time being missing again. But in this case, they're not missing completely at random. They depend on age and obesity. Now what happens when I do the complete case analysis and ignore the people whose failure time is missing? Missingness wasn't random. It depended on age. If I'm going to see bias, I certainly ought to see it in my coefficients for age. And here's what I get. This is what I get if I analyze all the data where nobody's failure time was missing. They were all ascertained. And now I delete 17% of the observations where the probability of being missing depends on age. 1.226 and 1.216. Those are the same numbers. Even if the probability of being missing depends on the covariates, I do not get bias in my analysis of failure time. I can get an unbiased estimate of how long people will live as a function of their age at entry or any other predictor, even if the missingness depends on the predictors. So that's an important thing for you to know, and it's going to hold for all of the survival analyses we do And in the rest of this class, if the data is missing and the missingness depends on the covariates, there's no bias. Okay? The reason is that the missingness depended on variables that we measured. It depended on age and obesity in the example I just showed you. And we control for age and obesity in our regression. And that makes it okay. That's why they're not missing completely at random, but they are missing at random conditional on the observed data, in this case, the covariates, which were observed. What if they're missing and the missingness depends on some variable that I didn't measure? Then you're screwed. So let's take a look at that. What we're saying is if I had two people who were matched on all of the covariates, the same age, the same value for obesity, the same sex, the same race, etc., and one of them was missing and one of them wasn't, are their survival histories the same? If that's true, then that's missing at random, conditional on the observed data. If it's not true, then we're in trouble, right? Because the people who we don't have the observations on are different in a way that we can't capture with any of the covariates that we have. And that can introduce bias. And let's take a look at that. So what I'm going to do is I'm going to make the missingness depend on the outcome, on the age at which the people died. Why? Because I'm pretty sure that the age at which people died depends on variables that I didn't put in my regression analysis, in addition to the variables that I did put in my regression analysis. And so this is a way to capture that scenario. Some of the probability of being missing will be related to the unexplained variation in the age at death after controlling for the covariates I have, presumably because it depends on other variables that I don't have. So the probability of being missing depends on the outcome, on age at death. And now, look at that. We're starting to see some significant differences in the coefficients that we get for some of our variables. Presumably because these omitted predictors of survival are correlated with some of the variables that I had. We didn't control for them, we have confounding. So if the missingness depends on variables you don't have, if the missingness depends on the outcome, then the data is not missing at random and you're going to get bias. However, that's true in Cox's proportionate hazard model as well. So the fact that this messes up our analysis of life expectancy, of failure time as the outcome, that's not why we do a Cox model. And if it's missing conditional on the covariates, we didn't see any bias. So why don't we do this analysis? After all, age at death is what people want to know. So does their life insurance company, of course. And so if we have uninformative censoring, why not do that? So I took the analysis that we did with the linear regression in the complete data set, no missing, and I looked at the residuals. Right? We did a linear regression, we have residuals, and this is the distribution, this is a density plot of the distribution of the residuals. This is not normal. Not only are these residuals not normally distributed, they're skewed. I have a long tail here, right? There are some people who die young, right? And it's, it's bumpy. This is a funky distribution. And you might think, well, this is because you only had 4,000 people. It would smooth out if you had more people. But I looked at 3 million participants in Medicare in New England, and I looked at the distribution of their age at death, and it looks like this. I mean, the bumps are a little different, but it's bumpy. The distribution is strange. Well, so maybe there's some sensitivity to the fact that the distribution isn't normal, particularly because it's not symmetric, it's skewed. What if I did something that was more flexible? When we talked about generalized linear models, I mentioned the gamma distribution. The gamma distribution can model skewed data. Skewed is one of the forms that the gamma distribution fits pretty well. Suppose I say, okay, it's a skewed distribution. Let me fit the same model. I'm going to say link equals identity, right? I just want a regular linear regression. The expected value of age at death depends on that, but the distribution is gamma. Here's what I get in the gamma model, and here's what I get in the linear regression. These numbers, are changing a lot more than they did when I had missing data. The results that I get are sensitive to how I specified the distribution of the residuals. And in fact, the distribution of the residuals is pretty strange. And so this creates some uncertainty about what the true effects are and what the hypothesis tests are. I mean, if I have a biased estimate of the regression coefficient because of misspecifying the distribution of the residuals, my p-values can be wrong. My confidence intervals cannot be correct. And this, I'm going to argue, is the real reason that people in epidemiology tend to use Cox's proportionate hazard model and not that all of the failure times are not observed. Because if the failure times are not observed, but the censoring is non-informative, things are just fine. That creates no bias in the analysis. Informative censoring does, but it also does that for the Cox model. The real issue is that the distribution of failure times is somewhat strange, and there's no historically, there was no good way to capture that. Now, in more recent times, we have developed ways to fit failure time models that don't make assumptions about the distribution of the residuals, and people have started to use that. But the main reason, if you don't want to do those fancy things, and we won't get into that in this course, for fitting Cox's model is that the results are kind of sensitive to the assumptions that you make about the distribution of the data. So what can we do if the results are sensitive to that? Well, at any given time, I know how many people died in that time interval, and I know how many people in my cohort were still alive and therefore at risk of dying in that time interval. I can divide those numbers and calculate a rate, right? And I can do that at any given time, and I so far said nothing about the distribution of that rate. I can also, at any given time, look at how many people are still alive at that time versus how many people started out in the cohort, and I can calculate the survival probability at that time without making any assumption about the distribution of survival times. It's just, yeah, there were 3,000 people left alive out of 4,604. Probability of making it to this follow-up year time is whatever that ratio is. And so that is why we tend to look at these things and not at the time to event itself. Because there are ways of doing this where we don't have to pay attention to the distribution. We can estimate these things in a distribution-free way. So we can calculate these two things without saying anything about their distribution. And so in the next talk, I want to continue on discussing what we can do using these survival rates and these rates of failing. Thank you.